Okay, now we're good. Glad I checked. All right, so we talked last time about these common antiderivatives we should already know walking in, and that is antiderivative of secant squared of x dx is tangent x, and antiderivative of secant x tangent x is secant x. Now, in the previous part of this section, we were using the fact that we knew the antiderivatives of sine and cosine, which are very straightforward and easy. But when it comes to tangent and secant, the only way we can use, I guess, a common formula is if we see somewhere in the integral a secant squared, or we see a secant x tangent x. Then we can go backwards, right? All right, let's get to the strategy. All right, so just like we had before, we're going to look at our integral. And it says if we have tangent raised to some power, m, and secant raised to some other power, n, where you have an even number on the secant, then we're going to use the Pythagorean identity. We're going to factor out a secant squared. Okay? And then we'll be left with some even power of secant, and we can use the Pythagorean identity to rewrite it. So it's very much the same procedure as sine and cosine, it's just we're using different identities. Right? So on the board over here, I'm going to put our identities. We have this identity here, which we'll be using, right? 1 plus tangent squared x. And then tangent squared x is equal to secant squared x minus 1. So those are the main ones we're going to use today. All right. Now, if we see secant and tangent with an odd power on the tangent, so the first method is if we have an even on the secant. This second one is if we have an odd on the tangent, then we're going to factor out a secant x tangent to x, and then we will proceed with this Pythagorean identity. And it tells us what our substitutions will be. So let's just work this first example. All right, let's try this one. All right, so we have here tangent and secant with powers, right? If we go back up to the steps, on the first part here it says if n is even and n is the power on secant. Do we have this? That's what we have, right? Secant is to the fourth power. Secant has an even power on it. So it's telling us we need to factor out what? A secant squared. Okay, so let's factor out a secant squared. So I need to turn this into secant squared x times secant squared x. That's just me rewriting secant to the fourth. And now, just as before, the thing that we factored out should be the part that's going to be the du in the substitution. So this right here should be our du. Do y'all see that? Which means u would have to be what? What substitution would we have to make for u here? Tangent, right? Because the derivative of tangent of x would be this, right? So we're kind of like getting there. We know that our substitution needs to be tangent x. We know that the derivative of that would be secant squared x dx. So we'll be able to replace that with du. We'll replace the tangent to the fourth with u to the fourth. The only issue is this secant squared. What do we replace it with, right? And we can't use this because this has dx in it. So this is where the Pythagorean identity comes in. We need to go and use the Pythagorean identity to rewrite that in terms of tangent. And then we'll replace the tangents with u's, all right? So we go, I'm going to just write it all out still. Tangent to the fourth x times secant squared is going to be replaced with 1 plus tan squared x. And then we have our secant squared x dx. And now let's make the actual substitution. So last class I was able to keep the little sticks here separated, but I don't remember which of these stacks I had already called on. So let me see. Kim, I called you last time, right? Did I call you last time? You sure? James, I called you last time?
Yes.
Okay, yeah, I think you're right.
I take a shot at it.
Okay, go ahead. I just want you to rewrite. What's the integral rewritten now?
Let's see, u to the fourth.
U to the fourth.
And then would that one be du?
This one?
Yeah.
Is that du?
It's not du, but it's the same
It'd be 1
thing.
plus u
It'd just be
squared.
1 plus u squared.
1 plus, and then remember, tangent's being replaced with u. So 1 plus, so in parentheses, 1 plus u squared there. And then this piece
Would be
is your du. There you go. And then distribute. So distribute the u through. So u to the fourth plus u to the sixth, right? Not eighth. And then now antiderivative. So the next step is where we'll pick up the plus c, right? Right, because we still have to actually take the antiderivative. So 1/5 u to the fifth plus 1/7 u to the seventh plus c. Then we replace all our u's, okay? So u gets replaced with tangent. Tangent to the fifth x plus 1/7 tangent to the seventh x plus c. That should be it right there. Do you all see how this is similar to what we have already done? It's just because we're working with secants and tangents, it's not as simple as peeling off a cosine or sine. You have to peel off either a secant squared, because that's a derivative of tangent, or you're going to peel off a secant x tangent x, because that's the derivative of secant. Now, we haven't done that yet. This is an example where you peel off a secant squared. Yes?
For the second line, you could have rewritten it as a tangent to the fourth x, parentheses secant squared, right?
Tangent, right here. Rewritten this as tangent to the fourth and then secant squared squared.
Right.
You could, but the method says you want to peel the secant squared off because you want that to be your du. So I guess here's what you're saying. Let me write it the way you're suggesting. If I rewrote that like this, I agree, okay? I agree that that's true. Does everyone agree that that's true?
Yes.
Okay, but here's the problem. If we do it that way, then if we say u is tangent x, right? Then du is secant squared x. You have to replace, you can only put a du wherever you see secant squared x times dx. This is not secant squared x times dx. It's secant squared x squared times dx, right? So you cannot replace this with du. That doesn't work. Does that make sense? So that's why you have to peel it off, separate them, so you get the secant x squared, secant squared x dx all by itself. Any other questions? Yes?
So I guess that's the one reason why it would make it different than when we were doing cosine and sine. Because last class we were writing it as cosine squared x to the second power.
Well, that's the part that we were writing as cosine, whatever, squared, was not the part we were peeling off. It wasn't the part we peeled off. It was always the part that was not peeled off. So like here, I could have replaced this here with tangent squared. I could have. And that's not going to impact anything because I'll wind up with u squared, which is still u to the fourth. So if you go back and look at all the problems we did, whenever we did like sine squared or cosine squared, that was never the part we peeled off. It was always the stuff that was left. Does that make sense?
Yes.
Okay. Any others? So if you see an even power on your secant, you're going to peel secant squared off, right? Why is it so important that you do that when you have an even power of secant? Like, for example, let's say, I'm just going to make this one up. Let's say we had tangent to the sixth x, and then we had like secant to the sixth x dx. If we look at that, why is it important why does this method say if we see an even power, we peel off secant squared?
Because you need that squared to be able to get your proper derivative.
That's right. So we know that we need a secant squared out here because that's the derivative of tangent, right? So that's important. However, There's something also that's more important, I guess, than that, and that is if we start even here and we peel off squared, what's still here? Even. And you need even on this in order to use this. Let me show you. Let's change the problem. Let's go back to the original problem. Let's go to this one. Okay? Look at that one right there. If you peel off secant squared here, it won't work. And the reason why, I mean, you can peel off secant squared, can't you? But what are you left with when you pull off two of the secants? Just secant, right? So you're like, okay, great. Look, I've got it right here. There's du. That's the derivative of tangent, right? So you're going to be able to say, all right, this is going to be u to the fourth. This is going to be du. But what about this? How do you get that to turn into something with u in it? You cannot use this, can you?
No.
No, because it has to be secant squared. So that's why it's so important that this start off even. If this starts off even, then when you pull off or peel off a squared, it's still even here, right? And then you can do this, use this somehow. All right, let's take a look at the next example. Tangent to the fifth secant cubed. So this is a perfect example of what I was just saying. You should not be looking to peel off a secant squared because you have an odd power on secant, right? But the method says that if you have secant and tangent together with an odd power, what does this say?
Save a factor.
With n odd, right? So now your odd is, you have an odd on the tangent, right? An odd on the tangent. Then what we're going to do is we're going to peel off what? A secant x and a tangent x. So we are going to peel off one of these tangents and one of these secants, right? So we're going to be left with tangent to the fourth x secant squared x times secant x tangent to x dx. And the whole reason we've done that is because now that secant x tangent to x dx is the derivative of what?
The derivative of tangent.
Secant. This is the derivative of secant, right? Everyone follows how I'm allowed to peel these off? I could have swapped the order, right? I could have done tangent times secant, but the formula for the derivative of secant is secant x tangent x. So that's why I did this. So this is going to allow me to make this substitution. I'm going to be able to make the substitution that u is secant x, and the derivative of that is secant x tangent x dx, right? So I know this is where I'm headed, which means I need to look at everything that's not part of this, right? I need to look at everything over here and somehow get everything over there in terms of secant so that I can replace them all with u's, right? But remember, the whole method started with saying that had to be odd, right? And if we peel one power of tangent out, then now it's going to be what? Even. If it's even, then I can use this identity, right? So I'm always going to be able to get tangent back to secant because it started odd and I peeled one off. I hope this is registering. So how do we? So are y'all clear? We're not worried about this at all.
Right.
Secant squared doesn't matter because secant's going to be u. So that's going to be u squared. That's du. It's just really this piece right here. We can't use the Pythagorean identity straight away because we don't have tan to the fourth in the identity. So this is where you would rewrite tan to the fourth as tan squared squared. Okay? So tan squared x squared and then secant squared x times secant x tangent x dx. And then you replace your tangent squared x with secant squared x minus 1. I'm going to come back up here. So in parentheses, secant squared x minus 1 squared, that's this, and then still times secant squared x, and then times secant x tangent x dx. At this point, we have everything we need. We've got the derivative of secant here, and everything else here has secant in it. So we should be able to convert this over to a polynomial in the variable u. So just replace all your secants with u, and we're going to be close here. So we should have here, let's see. I think you got it. U squared minus 1, right?
U squared minus 1
Squared times u squared times du. There we go. And at this point, you just probably have to do a little bit of algebra here. Just expand some things out. All right, so I'll go ahead and expand this. I'm going to do this right now. So that's u to the fourth minus 2u. I said u to the fourth. I wrote u squared. I need to fix that. Okay, this is u to the fourth minus 2u squared plus 1. That's this thing FOILed. And then u squared du. Next step, pass the u squared through. You're just trying to get it to a place where you can actually take the antiderivative. Now we can, right? So I'm going to skip a step. I'm actually going to plug the u back in now as I actually write down the antiderivative. So 1/7 secant to the 7th x minus 2/5 secant to the 5th x plus 1/3 secant cubed x plus c. Yeah? What do y'all think? Did I say something wrong? No? Oh.
Just saying it's funny when people go from like to the 7th power to the 5th power cube.
Yeah, you caught that? I caught myself to do it too. Cubed, yeah, squared. All right. That's it.
Is it just me or am I noticing kind of
It's just
a pattern?
you.
I was just kind of noticing a pattern of the step downs from the homework and Sine. And like, so basically it seems to me like if the powers of the two are separated by 2, so like gain 5, they end up stepping down pretty consecutively, so you'll start off with 2 higher powers of opposite sign. Off of the function, then it works down by 2 powers down, 2 powers down.
Maybe there's some. I don't think I've looked into it that much. Maybe there is. We can talk about it if you want afterward. Maybe there's something we can find in there. Okay, so on the first problem, we were able to do the first problem because secant was even, right? We were able to do the second problem because tangent was odd, right? So I wonder if we can make up a problem right now where neither one of those cases happen. We would need tangent to be what? Even. So let's go with tangent x, tangent squared x, right? And let's do secant what? Secant odd? Okay, so we're just making this problem up because if you follow the method here, do we have an even power on secant? No. Do we have an odd power on tangent? No. So what do? Multiply by 1? Like what one? Yeah, so maybe this is one of those weird. I just made this problem up, so let's see what happens. We already know we can't peel off the secant squared because if we try that, then we're going to need to convert everything to tangent. And if I pull secant squared off of this, I won't be able to convert that secant that's still there. I won't be able to convert it to tangent. If I do it the other way and pull, what would happen if I pull a single secant and a single tangent?
That works, secant x tangent x.
Yeah, but I'll be left with a, so if I pull off a secant and a tangent, right? Then that's going to be my du. And my u would then have to be secant, right? So if I peel a secant x here, that's fine. I'll be left with secant squared, and that's okay. But if I peel a tangent off of here, I'll be left with a tangent, right? And I can't convert the tangent to secant using Pythagorean. Maybe integration by parts, might go by parts. Okay, so whenever you run into a problem on something like this, one of the recommendations is to try and convert everything over to sine and cosine. Okay, let's just see if we have any hope doing it that way. So I'm going to rewrite tangent squared x, the sine squared x over cosine squared x. Everyone agree? Okay, now what is secant cubed x? Rewritten. It's 1 over cosine cubed x dx, because secant is 1 over cosine. Okay, that seem reasonable so far? All right, let's see if we can go anywhere with this. This would be sine squared x over cosine to the 5th x dx. Yeah? Can we do anything with that? And we could bring cosine up as cosine to the -5, but I mean, we're dealing with an integral that has sine and cosine in it now, right? And with sine and cosine, there were like steps that we were supposed to follow. So let's go back up and look at those steps. With sine and cosine, we're saying, okay, do you have cosine to an odd power? Yeah, we kind of do, but that's, remember, this is in the denominator, right? So it's actually like -5 power. Would you all agree with that? It's actually -5, so that's not quite the same. Because look at the way this is written, it's cosine to the n, right? We're kind of assuming that's up in the numerator. Do we have sine to an odd power? No, we don't. All right, what if one of them is even? You have to use half-angle identities, right? So this one's a bit messy. So I would never present something like this, I don't think, not on a test. All right, this would be more of like a bonus sort of problem for you, because it might go with something like integration by parts. You just have to figure out which one to pick. And so really the moral of the story is this. That formula sheet that I gave you that kind of gives you the steps of what to do, it works for a lot of the cases, but not every case. All right? There's a case where it doesn't. And can y'all see how we're kind of stuck here? Like, it would be real nice to let u be cosine x and du be, what, negative sine x dx? Because I see something in its derivative. The problem is the derivative is being squared. So it's trapped, isn't it? It's not off. Now, could I peel one of the signs off? Yeah. I could, right? But then there's a problem, I'm going to have to somehow do something with that sign that's still there. Here, let me write it down like this, just so you can see it. Like I could do that, right? And then if I make this substitution, this could become u to the 5th on the bottom, right? Here's du. I'm off by a sign. I could pull a negative out. Yeah? Mm-hmm. Yes? So this could be rewritten right now. U to the 5th on the bottom times this part right here, which would be negative du. But the problem is rewriting this. And you have to write that in terms of u. So how would you write it? Yes?
Whenever you go ahead and say like du, you divide by negative sine.
Over here?
Right.
Mm-hmm.
You get rid of it.
I'm not sure I'm following you. We have here sine x dx, so I don't mind seeing sine x dx. Right? Like that matches that. I'm just off by a sign, so that's why I put negative du. And then this cosine is my u, so u to the fifth. The only issue I have is this right here. I need to rewrite sine x in terms of u. It can't be in terms of x. Everything has to be in terms of u, or everything has to be in terms of x. It's one or the other, but not both. How about this? Could I do this? Look at that equation right there. Not arcsine, sorry. Could I do that? Could I take inverse cosine on both sides here? So if I take inverse cosine of u, I get inverse cosine of u. If I take inverse cosine of x, I get x. So I have an expression for x, don't I? X is arc cosine of u. So I could replace that x with arc cosine of u, which means this top would turn into sine of arc cosine of u. Okay, so we are going down a rabbit hole here, aren't we? Like this is starting to get pretty weird. So I'm going to stop because the whole intention of me putting this up here was to see what would happen if we put a scenario up there that's not covered on that sheet. We run into a problem pretty quickly, yes? Okay, so I said pretty early on in this class that if you were to like take all of the functions in the world, right, in the universe, and put them in a bucket and reach in and grab one and put it on the board and say, can you find the antiderivative of that? The probability of being able to do that is essentially 0. All these problems have to be very specially tailored to be doable, right? So here's an example of one that so far we don't have anything. Now I do think it'll go with integration by parts. Now let's look it up, okay? Just for the sake of, I don't want to leave it as an open question. Let's see just how difficult this would be. You can always tell by going to Wolfram Alpha and just typing it in. If we get something called an error function, then we'll know we'll know it can only be done with a power series. Okay, so we want to integrate. What was it? Tangent x, tan x squared times secant cubed x. It should be smart enough to understand what I'm saying. I can see it here. Let me see what it has. Some half-angle identities in here, logs. But I don't see any error functions, so that can be done somehow. All right, there's some path to an antiderivative there. I'm gonna guess some sort of integration by parts. I don't know. I don't see it right away. So, okay. So you see how complicated this gets very quickly? Yeah. All right, let's move on. That reminds me of, well, no, never mind. All right, so last class, those are the only two examples we're doing with tangent and secant. And I did the first two of those last class, didn't I? I showed you how you can find the antiderivative of tangent by rewriting it as sine over cosine, and then using basic u sub. And I did secant x by showing you this weird 1 that you multiply by. You know, and that you would never have come up with that, but that's... So if you look in your formula sheets, both of those are in there. The antiderivative of tangent's in your formula sheet, the antiderivative of secant's in your formula sheet. Okay, so how about secant cubed? Let's try that one. Can we use the little cheat sheet for this? Does it tell us how to handle this? It doesn't, right? Remember, it says up here that if we have secant even, we can do something. But here we have secant odd, and we don't even have a tangent, do we? So we don't have a method for this yet. I mean, we don't have anything we can do. But this one actually does work out real nice.
Can you break it up?
You can break it up as secant x times secant squared x. Okay? And then we can use integration by parts. So if you were thinking, and I'm going to call someone here. If I'm telling you this goes by integration by parts, then Shay? It's kind of ironic that you suggested integration by parts on the previous problem, and then now it's integration by parts on this one.
I would pick
Like, what would you rather take the antiderivative of, and what would you rather take the derivative of?
secant squared, the derivative of that.
So you want secant squared
Yeah.
here? I agree. Does everyone agree with that? Secant squared x dx seems like a natural candidate to put here because the antiderivative of that, we know, is just tangent, right? Now, that forces you to have to put secant x here. So if we complete the table, we know that v is just tangent x, and du is secant x tangent x dx. So whenever I do my table with integration by parts, I'm always thinking to myself, what's voodoo look like? Can I integrate voodoo? Can I integrate voodoo, right? That's what I'm thinking. And I don't know. I'm not sure yet. So here's where we are. We've got secant x tangent x. That's ultraviolet, right? Minus integral, then voodoo. So can I write it this way? Secant x tan squared x dx. So our new integral, here's our new integral. Is this any better than what we had to start with?
Not really.
Not really, right? I mean, you did gain a tangent, right? And we do have methods for tangents, but we need an odd on the tangent, and we have even. Go ahead.
Double or multiple times breaking it in parts.
Like do parts again?
Yes, sir.
Okay, so if you did parts again, maybe it'll go. What would you choose for your u and your dv? And the thing you want to be careful with is you don't want to do the opposite of what you did here. So you don't want to choose your u to be tangent, because that'll take you back. And see, this I think is where you get hung up on the integration by parts on the second time, because you're not quite sure what to put where. I guess you could put, maybe you could put secant here, because we did come up with a formula for that last time, but it involves natural logs, right? Was there a question?
I was just trying to say, can we use the Pythagorean?
Okay, so you want to do Pythagorean for tangent squared? Is that what you're saying?
Yeah.
Can we? Are you allowed to?
I'm
Yeah, no, I'm asking you back. Can you do that? Can you replace tangent squared with secant squared x minus 1?
Yeah.
Sure, it's algebraically, that's fine. So will it work? I don't know, let's see. I just feel like this is problematic because of the choices, all right? The choices we would have to make. Here it was a little more natural after you break it up to have this be here and that be there, and this seems reasonable. So rewriting this becomes secant x tangent x minus integral secant x, and then now secant squared x, right? Minus 1 dx. Okay. This was your idea, so yes?
Don't you square the secant squared x minus 1?
What do you mean square it?
Because it's a 10. Oh, never mind.
No,
I'm sorry.
yeah, so it went straight over, so we're,
Never mind.
no, you're good. That's what you wanted? All right. All right, you're going to have to lead us down this path then. So what would you do next then? Okay, so just multiply it out? Okay. So if I do here and here like that, then I get secant cubed x minus secant x dx. That's where we are, right?
I don't see it another way.
You're there. You're there. You're there. This is kind of a weird one, though. So because there's subtraction here, you can split this into two, right? You can do these individually. Do you know the antiderivative of secant x by itself? We did at the end of class last time, right? So we can handle that by itself. Yes? This one we can't handle, but
We could do your substitution.
no. This is the integral we're actually trying to find. And so it has appeared on the other side again, hasn't it? We had this happen. Yeah, this is the one where we can now move that one over again. Okay, so let me just kind of rewrite it all right? Here's where we are. Okay, we're here, right? We're here. Yes, we're here. So this is equal to secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. So all I've done is I've broken this into two separate antiderivatives. I've applied the negative to here and here so that we get a minus and a plus. And that's where we are, right? Okay, now, the antiderivative of secant x. We did this last class. It's natural log secant x plus tangent x, something like that. That should be in your sheet somewhere? Okay.
That's natural log.
Secant x plus tangent? Yeah. Okay, so look, I'm going to go, this is the line we're at, but I'm going to start from the beginning. This is what our original integral is, right? Then we have that equals this, right? And now I'm going to put these two up here. So this one would become minus secant cubed x dx. And then you just told me that the antiderivative of secant x, excuse me, from last time is natural log of secant x plus tangent x. I did do that last time, right? So this one we got. There it is from last class. So what should I do now? Add a single integral to both sides. So I'm going to add on this side this integral. And then I'm going to add that integral on this side. How important is it that this is a minus sign? It's vital. Because if this was a plus, what would you be doing on both sides? Subtracting, and then they would go away, and then you don't have any information about the integral, and that would have been something's wrong. But the fact that this is minus means you can add it, which means it doesn't go away on that side. All right, so next line will be these two added together, which is two of them, right? Two of these integrals is equal to secant x tangent x plus natural log of secant x plus tangent x. I'm going to go ahead and put plus c now. This was like, we did this problem, a problem like this when we had like cosine with e, and we said it appeared on the other side. Pardon?
Don't you carry the negative over?
What negative?
Natural log, secant plus tangent x?
No,
What negative?
right there.
Oh, right here. There was a negative in front, but then there was a subtraction inside, so it went in and became a plus. Yeah, because we replaced tangent squared with secant squared x minus 1.
Yeah, I see what I did.
One more step and we're done. Multiply both sides by 1/2, or divide both sides by 2. So if we divide this side by 2, we can put a 1/2 in front there, and a 1/2 in front there, and we don't have to divide c by 2, because c is still just a constant. Okay, so the antiderivative of secant cubed x is 1/2 secant x tangent x plus 1/2 natural log of the absolute value of secant x plus tangent x plus c. Weird problem. But nice, right? Any questions? I don't know. That problem right there is more to show you like now you see how secant cube went, you know, like that was integration. First we had to try integration by parts, split it and try it. And then after integration by parts, it turned into one of these weird ones after a Pythagorean identity, right? it turned into one of these things where it appeared on the right-hand side again. So I don't expect that sort of thing as a question I'd ask you on a test. Now, if I asked you to do secant cubed, like if I gave you this exact problem, that I could expect on a test. But like for you, to give you some random problem that works out like this, I don't think I'm going to go there. What if it was secant like to the fourth? Well, I don't know. We'd have to go there. Yeah. Yeah. But remember, I mean, it's very easy for us to put a problem up here we can't do. All right? It's very simple for that to happen. So we'd have to just mess with it a little bit. See what happens. Because of time constraints, I'm not going to go down that road right now. But secant to the fourth, you could go secant squared. Then you could try maybe integration by parts. It may go easier than we think. All right. Oh, wait, hold on. To the fourth. No, hold on. Yeah, you just go peel off a squared, and then the other one use Pythagorean identity. Because if it's even, you peel off a squared, the other part's going to be even, so that'll be clean. That'll be clean. I'm sure there's a few like that in the homework. Okay, y'all ready? We're moving on. All right. So if we were to just summarize briefly what we have covered, you walked in day one, there are certain functions you could take the antiderivative of because you knew them from Cal 1. That was the first thing. Then we learned the power rule, right? Which we've been using a bunch. And then after power rule came U substitution. U substitution means you try and find something and its derivative appearing within there in the integral at the same time, right? We've used U sub we use it kind of all the time now, don't we? Like U sub seems to be taking place quite a bit. And then after U sub, we learn integration by parts. And that's your first test up to there. Now we've added to that trig integrals, which means if we see like combinations of cosine and sine, there's certain ways we can go about them. If we see certain combinations of tangent and secant, there's certain ways we can go about them, so long as it looks a certain way. Now we move on to what are called trigonometric substitutions, or we call this trig sub. Trig sub. You go to the tutoring lab, you're like, I need help with trig sub. The tutor should know what you're talking about if they've taken Cal 2, all right? Trig sub, not U sub, trig sub, right? So this is a very strange thing that we're about to do, right? It's very strange, but it's very powerful. I would say, historically, teaching this class, I've been teaching it for a very long time. This is probably where the wheels start to wobble a little bit for people. If it's not wobbling already, okay, like this is where it starts to, because these problems are just long and tedious and just, ugh. All right? I mean, so just be prepared. It's just gonna, if it seems like this is a lot, it's because it is a lot. All right, so what we're gonna do is we're gonna try and tackle a certain type of integral, all right? And the type of integrals that we're gonna look at are any integrals that have this in it, this in it, or this in it. So if we see anything that looks like that inside of an integral and we're having trouble with the integral, we're going to try this thing called trigonometric substitution. Let me give you some examples of how things like this would appear in an integral. So just so you're familiar with what they look like visually. So how about this problem right here? How about that? Does this integral have one of these three formats in it?
Yes.
Which one? Top, middle, bottom? Top one, right? So A here is a constant, all right? A here is a constant. Do we have a constant squared minus the variable squared under a square root? Absolutely, it's right there. Now, let me ask you in this problem, what would the a be in this problem? What would a be?
9 or 3.
3. Okay, a is 3 in that problem because this is 9, right? In the format or the formula over there, it's a squared. Okay? So a problem like this might be trig sub, might be. All right? How about this one?
No.
Does that look like any of those?
No.
Yes. That's-
Well, wouldn't that have to be 25?
Well, would it? So the question is, do we have the square root of our variable squared plus a number squared?
No.
Well, is 5 something squared?
No. It would have to be 25.
How about the square root of 5? What's the square root of 5 squared? 5. So this is that format with a being root 5. See? So you can actually have any number here. Doesn't have to be a perfect square. It's just a will always be the square root of that number that you see. All right? So this looks a lot like this, and so we would be using perhaps trig sub for this. Got it? Let me ask you something. Algebraically, are these two different?
Yes.
They are different. They're off by a sign, right? So could you factor a negative out of this and make it this? Like, could I do this? Is that legal to pull a negative out of here and rewrite it like this? But I have a negative. These are not the same thing, right? This negative here is different than this. Can I pull the negative out of the root? Cannot. It's imaginary numbers. Okay, we can't go there. We're not going to go there in here. So these two expressions are distinct from one another. Now this one, you could flip the order around. It's the same thing, right? Okay, but these two, the order matters. So if I go back to this problem and I change it to x squared minus 9, do we still have a being 3? Yes? But it looks like this one, not that one, right? So these are our 3 different scenarios that we're going to work with. All right, y'all ready to see how this works? Question? No? Okay. All right, so let's see what it is that we're going to do. We're going to start with this first one. All right, so if we see this, if we see this right here, we are going to make a substitution of x equals a sine theta. Now this is what I said when I said, or this is what I mean. Shut up, Robert. Okay. Earlier I said this is going to be weird. What I mean by that is we're going to take an expression that has some number here minus our variable x squared, and we're going to replace the x with a more complicated trigonometric expression. But great things are going to happen. All right? So let's see algebraically what happens if I replace that x with a sine theta. Okay? So let's take this. Let's replace x with a sine theta. We get a squared minus now x, which is a sine theta, but I need to square it, right? So when you square this, you square the a and the sine, right? They both get squared? I mean, it's a sine theta squared, but because there's a product, you go the square on both of them.
Right, that's correct.
Okay, so now when we look at that, what's a common factor between these two?
A squared.
A squared. So you can pull an a squared out underneath the root. What are you left with when you factor out the a squared? 1 minus sine squared theta. Does that look familiar? 1 minus sine squared theta is a Pythagorean identity. That's cosine squared theta. So that must be square root of a squared cosine squared theta. And what does that equal to? Well, a cosine theta. Right? So let's just kind of shortly recap what just happened. If we see this complicated square root expression, if we replace the x with a sine theta, that complicated expression turns into that expression, doesn't it? And if I asked you to integrate something like this, I think you'd be much happier than integrating something like that. Would you agree? Because this is just a cosine. We can integrate cosine all day. So this particular type of trigonometric substitution allows us to take something ugly and turn it into something doable. Yeah? This would have worked for any a, right? Like whether or not that's like, 9 there or 5 or whatever it is, it's always going to turn into this, isn't it? Okay, now let's actually look at one more thing. We know that this expression is going to appear in an integral, right? I mean, that's where we're going with this. This is eventually going to appear in an integral. And what's always sitting at the end here? Dx, okay? So if we go and we switch this expression over from this to turn it into this, what's our new variable? Theta is the variable now, right? So we've gone from x to theta. So in our integral up here, we know this is going to turn into something with theta in it, but we still have a dx there. We've got to get that dx to turn into something with theta also. So what we can do is we can come back to this, and we can take the derivative on both sides. Basically, this left side becomes dx. Let's do it this way, dx d theta. Let's take derivative with respect to theta. This is dx d theta. This side is a cosine theta. Right? A is a constant. Derivative comes for the ride. Derivative of sine is cosine. And then I can multiply both sides by d theta, and I have an expression for dx. Okay. Let me recap all of that. Let me just recap it all right? I'm going to erase some of this. So if we see square root of a squared minus x squared, we're going to let x be equal to a sine theta. Then we know that the square root of a squared minus x squared, if we were to algebraically simplify it, we know it turns into a cosine theta. We showed it, didn't we? And that'll happen every single time. And we know that dx can be replaced with a cosine theta d theta. And this is everything you need to know if you see this type of situation. That the square, you're going to make that trig substitution. You know that that big complicated root thing's going to turn into this, and you know that the dx is going to turn into this, and then you look at that new integral, and hopefully you can handle it. I think you should see an example. Yes? Okay. So let's try this one. Let's just go with this. Let's go with that one right there. Okay, Priscilla. Does this fit the format that we need?
Yes.
Okay, the format that we have
Is a squared minus x squared.
square root of a squared minus x squared. All agree? Okay, Priscilla, what is a for us?
3.
Okay, a is 3. Now, let's start everything out. That was just identifying which one it looked like and identifying a. Let me point something else out before we get too far ahead of ourselves here. Can you do that integral any other way right now? Like, is that just a basic, you knew that from Cal 1, or is that a basic U sub? How about if I would have what if I put an x right there? That's a basic u sub. Why? Because if you let u be 9 minus x squared, what's its derivative? Negative 2x, right? Which you would have it out here. You'd be off by a constant. So just by having an x there, we can do the problem. You take the x out, we can't. That little subtle little thing makes a huge difference in the problem, right? So we don't want to just automatically see a square root and be like, oh, it's trig sub, trig sub. You always want to look, is there something else you can do? Integration by parts. You would have to make your table and pick a u and a dv, right? Like, what's your u, what's your dv? I'm not sure that gets you anywhere. Do you agree, Priscilla? I mean,
Yeah,
like,
I agree.
but it does look a whole hell of a lot like this, and this looks promising, yeah? Okay, so Priscilla, what is the substitution I'm making? I'm going to replace x with what?
You're gonna replace x with a sine theta,
And a for us is,
and a for us is 3.
so we're going to replace x with
3 sine theta.
3 sine theta. Okay, Priscilla, without us actually going through any of the work, what do we know automatically this nasty root expression is going to turn into for us?
Or wouldn't it be 3 cosine theta?
3 cosine theta, right? Without having to do any work. That turns into 3 cosine theta. Now, just because I want to be somewhat thorough, why is this happening? Because if I replace that x right there with 3 sine theta, right there, and then I square it, then I get root 9 minus 9 sine squared theta. Then the 9 comes out, I'm left with 1 minus sine squared theta, and then that becomes 9 times cosine squared theta. That's all under root, and that turns into your 3 cosine theta. You don't have to show that every time, but algebraically you could confirm it does work, all right? At some point you're going to just memorize this. You'll have it memorized, okay? It'll happen, maybe in 2 years. But is this that sheet? What's that sheet I gave you?
Oh, no, that's.
Yeah, so on the bottom of this formula sheet, it summarizes some of this, okay? You'll have to look at it yourself. It tells you what format to look at. It'll give you this, and it'll tell you that this is your substitution. Okay, so that will be given to you on this formula sheet. If you see this, here's your substitution, or this is your substitution. The formula sheet does not give you these two things. So these you have to kind of remember. Where did I take that from you? Okay, let's keep going. Let's move on. Hogan?
Yes, sir.
All right, so Hogan, Priscilla got us to here. She recognized it and then told us this and then this. What else do we know automatically right now? We knew that this would be our substitution. We knew that that nasty root would turn into this, and we also know that dx will turn into what for us?
The d theta over there, sir?
Mm-hmm. So it'll turn in, for us, it'll be 3 cosine theta d theta, right? 3 cosine theta d theta. And that one you don't actually, you just take the derivative of that, right? Just take derivative of that, and that's this line. This is really the only one you have to really remember. All right, Hogan,
Yes, sir.
I want you to rewrite the integral for me. So what does this become? Look at the information we have here.
Just integral.
This is it, right? Replace it with?
3 cosine theta.
That's it, right? So we're going to rewrite this integral. That's going to become 3 cosine theta. Right? Is that pretty straightforward? You're just replacing it. And then